Hi, I'm Texas State Aquarium's Education Manager, Nicole Gertner. In January 2024, I worked alongside Dr. Keisha Barr, Assistant Professor of Marine Biology at Texas A&M University, Corpus Christi, at her lab on Coconut Island, Oahu, Hawaii, in a study that focuses on the characteristics of coral, their growth patterns, and how to preserve the species. Researchers cannot microscopically see the growth process and still do not know what causes calcium production in corals, which is the process that helps them grow. Dr. Barr's series of coral experiments, known as the proton flux hypothesis, set out to determine who is the frontrunner of coral calcification or coral growth. This project between Texas A&M University, Corpus Christi, and Texas State Aquarium began in January of 2021 and is currently being loaded with data from various researchers within the program. Corals are pretty dynamic organisms that can act differently during the day than they do at night. During the day, due to sunlight, the corals are growing because they photosynthesize and produce algae, which they feed on. But overnight, while they feed, the corals do not show much calcification and can even show a loss of calcium. With no daylight, there is no photosynthesis occurring and no energy being created, which can result in dissolution or the loss of calcium carbonate skeleton. The overall project has been going on for the last 4 years and has had up to 30 researchers collecting data, from biologists and engineers to environmental scientists and chemists. With the latest information being gathered for the 24-hour experiment, the main question for these studies is, what creates coral growth and what drives calcification? Mesocosms are the large, controlled tanks where the coral is placed, and experiments are monitored. Measuring the skeletons of the corals is imperative to studying any changes that may occur. The density data of each coral skeleton is also taken using the simple equation of density, mass over volume. Characteristics and composition of the corals are also documented, noting any changes that may occur during the 30-day cycle of the experiment. Another growth measure taken after the 30th day is to freeze, then cut the skeletons in half to obtain a subsection of the coral, looking under the microscope at the bands that form daily, almost like rings of a tree. 2 species of coral studied were pulled from a depth of about 1 meter or 3 to 4 feet. Controlling the simulation by pulling the subjects from the same depth that will be studied is imperative in getting the most precise readings. One of the areas of measurement includes how much growth is taking place. This is made visible by using a pink biological stain that is safe to the coral species. By dyeing water surrounding the corals, the newest growth is detectable due to the color variance, with the new growth being white in color. To produce a simulated water environment, the water temperature, the amount of dissolved oxygen, the salinity, the pH, and the alkalinity are all meticulously measured and recreated. With at least 2 researchers on site, the 24-hour experiment begins with gathering the weight and measurement of all the coral subjects on day 1. From each mesocosm, water samples are pulled and tested every hour on the hour for 24 hours on day 1 and day 30.
So what are you working on right now, Dr. Barr?
Right now, I am analyzing some water samples that we've taken every hour on the hour to see how the different tanks with the corals in them, how they're responding over a 24-hour period. So each water bottle corresponds with a certain tank. What we're trying to do is first I'm looking at these samples of the water going into the tanks, and then we look at the water coming out of the tanks so we can see how the corals are changing the water chemistry. So in order to do that, we have to process every single water sample every hour to analyze the chemistry of the water.
Do you get any breaks?
No breaks. For 30, it's really 26 hours, but with setup and breakdown, it's about a 30-hour experiment. But the really cool thing about it is a lot of people just look at what the corals do during the middle of the day, and they're actually a lot more dynamic throughout the night. So we want to try to capture what they're doing at night as well, and not just during the day.
On day 30, the corals are individually weighed and measured again to determine and document the growth rates for each mesocosm. These 30-day, 24-hour experiments are done 4 times per year, or 8 full days per year. The variables taken will help researchers understand the conditions that change the production of calcium carbonate. All mesocosms are controlled differently and will result in the coral producing varied weights and measurements. Because calcification is measured by pH and alkalinity, researchers will vary the pH levels per tank to gather different comparable data. They have learned that adding carbon dioxide to the mesocosms and decreasing the pH leads to an increased level of protons in the water. By manipulating the hydrogen ions, the growth rate of coral will vary. To manipulate the availability of carbonate and bicarbonate, researchers change the alkalinity of the water along with the pH levels to get varied water levels. Coral tissues are frozen, cut into fragments, and the tissue is removed to measure the coral's liquid protein, algae levels, and levels of chlorophyll. The skeleton is measured in composition and weight to gather the density of the coral, and tools are used to measure the new white growth in comparison to the pink stain. If we don't know how corals grow, how can we make sure that they continue to grow in the future? If we learn how that happens, we can use advanced technologies to preserve this species and potentially help all species that rely on calcification. Is byproduct from proton production limiting coral growth? Some believe that carbonate is the ion that corals use for calcification. Is growth limited because there is less carbonate in the water, or because there are too many protons in the water? These two questions represent competing theories at the moment. While I was visiting the island, I was able to snorkel and enjoy the thriving coral reefs that Dr. Barr is working hard to protect through her research. I learned from Dr. Barr that you can recognize a thriving reef with a distinct popping or clicking sound, and I heard this firsthand. We have had a fantastic series and are grateful to be partnering with the Heart Research Institute at Texas A&M University, Corpus Christi, working with Chair for Coral Reef and Ocean Health, Dr. Keisha Barr.